These are the upscaled and colorized lessons of Alexander Lippisch. Lippisch was a pioneering German aeronautical engineer renowned for his significant contributions to aerodynamics, particularly his work on tailless aircraft and delta wing designs. His career spanned crucial decades of aviation development, marked by a persistent exploration of unconventional flight concepts.
Today, we want to talk about stability and control of an aircraft. You know, it is often said that if you have an engine with enough power, even you could fly a barn door. Now, I must doubt that. Well, I couldn't make the experiment with a barn door right in here because I fear the barn door is too small for this place. But I could probably take this cardboard as a model of a barn door. And we can try to fly this barn door model. And you will see how it flies. Well, I think the barn door does not fly. Even if I give him a push, it makes only erratic motions and falls down, but it does not fly. See, this is an important point. Something which moves through the air, we call it fly. And some other thing, we say it falls or it is thrown. What's the actual difference? When something flies, then we expect to have a steady motion with almost uniform velocity, and where this thing which flies keeps the same attitude all the time. Something which is thrown might change its attitude, it might change its course and do erratic motions. Well, I can explain it in a very simple experiment to you. See, I have taken from my desk calendar 2 pieces of paper. The one piece of paper is just this one. You see, when we let it go, well, it makes these erratic motions in falling down, as you see with any piece of paper, you know. Now, if you fold some part of this up so that you get a special position of the center of gravity and shape it a little bit different, then you can make it flying. You see here? That means, what do you need for flight? You need stability of the motion. And on the other hand, if somebody would be in there and he doesn't want now to fly this way and probably around like this little model does it, but he wants to go another way, or he wants to go up, wants to go down, then he has to have, besides of the stability, he has to have control. So what you need is stability on the one side and control on the other side. Now when you think, which of the two is the most important? Well, on vehicles, as we use them like a car or a bike, we actually don't have stability. We just control all the time the car to go straight on the highway, or we control, for instance, the bike by hand or shifting our weight. So if we have an efficient enough control, we could all the time keep this flying thing on an even keel. The problem is this, that while we are on the car, for instance, we have to control only one motion sideways. But if you are in an airplane, then you have to control 3 types of motions, since you have 3 degrees of freedom. See, you have the freedom to go up and down. You have the freedom to go left or right. You have the freedom to go rolling. That means turning in the direction of your axis. Therefore, since you have 3 degrees of freedom, you need 3 types of controls. And it would be pretty difficult for somebody now not only to control this, which is probably done with a stick on an aircraft, but to control the up and down motion and to control the roll motion, all in one time. Therefore, finally, we came to the solution that the best is to make an aircraft stable in itself, inherent stable, and then control just its motion from there on. But originally, most people thought that flying, this time gliders, since they didn't have engines as yet, you would just need to shift your weight. Shift it forward and backward so you would control the up and down. They never thought about the control of the roll. And the first people who ever conceived this idea that you need 3 types of control for 3 degrees of freedom were the Wright brothers. Now they said we must change the incidence of the wings, the outer wings, so that we can turn in rolling over, because when we make a turn, then we have to bank against the centrifugal forces, which would throw us out. So first they thought the easiest way to do it would be probably to make a mechanism so that the wings could tilt and each wing would have a different angle of attack than the other one. But this was mechanically too complicated, would have taken too much weight. So they came to a better idea and said, why we don't take the biplane type and twist the whole frame. See, I have here a simple model, actually a replica of the first kite model which they tested. And see, they did not have any bracing across in here. They are just bracing in front, bracing at the back. And in this way, when you now make wires over rolls which are actuated by the pilot, then you can twist this without changing its strength. You see? And this type of warping the wings, they used all the time on their gliders. Now, I have here a very nice model of their 1902 glider. Actually, an exact model as the glider looked like. And we have even in here built in the controls as they used them. This is, now the pilot itself lays down on this lower wing and has in its hand the elevator control, which is this one. You see it move? So he pulls back and the thing goes up. Now he has a cradle where he lays in, and when he shifts this on left or right, then the whole wing warps. I hope you can see it. This warping is actually not very much what you need there. You see, when I warp it this way, then this angle is smaller, while this angle is larger. But they met in this way one difficulty. The moment you warp, for instance, this so that this angle is smaller and this is higher, that means that the plane would roll over this way. Then, due to the higher lift which you have here, you have more drag. And this more drag would actually try to turn the plane against the rolling. Therefore, they used, in addition to this wing warping, they used a rudder which is directly connected with the wing warping, so that when you push this wing down and have here more lift but also more drag, the rudder would counterbalance this more drag by turning the aircraft in this way. This very intelligent method of controlling an aircraft was actually the solution to the invention of the first flying machine. Now, most people would think that such a control in front for pitch, that means for longitudinal motions of the aircraft, would not be stable. You had to control all the time. Actually, that is not so. You can make an aircraft flying stable in pitch with an elevator, as we call it, in front or at the rear. And in both cases, you can obtain stability of flight. As I can show it you here. See, I have here a little tiny, flimsy model where I have the additional horizontal surface, the so-called elevator, in front. And you will see that this flies very nice and stable. You see? Now, if I take this wing and just turn it around, like this. You see, I have some clips down there, which I can push on this little stick. And then change the center of gravity by putting some little weight in front. So, and if I have it now, adjust it right, I think it should be, then you can fly it this way. You see? That demonstrates very simple that you can stabilize for pitch stability either with the surface at the rear or with the surface in the front. The main principle of this stabilization is this. The surfaces which are in front have to have the higher specific loading all the time. That means if you have a wing, for instance, which has 30 pounds per square foot wing loading, and you fly with an elevator in front, then the elevator in front has to have more than 30 pounds, let's say 45 or 50. If you have it in the rear, then you have to have less than 30. That means probably 15 or probably even nothing. This is the system of pitch control. And even if you have only a wing, a flying wing, you do still the same thing. See, this is the model here. Now, the surfaces in front are the surfaces at the center. The surfaces at the rear are the surfaces on the wing tips. Therefore, you have to have less loading on the wing tips than you have in the center, which you establish here by just warping this wing, as you see it here. When you look from the side, here we have a much less angle of incidence than we have at the center. And you will see it certainly flies nice and stable. See, there it goes. Now, at our conventional type of aircraft, we have now established the pitch control by surfaces at the rear, which is in many ways more practical. You have to have a long fuselage, and you have practically no loading on the surface, on the elevator surface, makes it more sensitive in flight. And I have here a very nice little model where we now can explain all the method and all the system of controlling an aircraft as it is today. You see, this is the seat which is open here. Let's say it looks like a glider. You sit here and you have this stick in your hand and you have your feet on the rudder bar. Now, with the stick, you control with forward and backward motion the elevator, which is now a flap on a fixed surface, which we call the stabilizer. You see, when I move this back, you see, then the flap goes up. When I move it forward, the flap goes down. Now, if I move this stick sideways, then I move the so-called ailerons, which now replace the old method of wing warping as it was done with the Wright brothers airplane. Since we have now stiff wings and we fly with much higher speed, which is necessary then to have stiff wings, then you couldn't warp these stiff wings. That would be very difficult. Therefore, we have a hinged flap on the outer part of the wing and move the hinge flap instead of turning the whole wing. And you see, when I move this stick now sideways to the left, then the left one goes up, the right one goes down. You see, this way. Now, if you fly this aircraft and you fly through gusty winds, what have you to do? You see, you just do nothing, then keep the stick in a vertical position. Then you do the right motions intuitively. You see, if a gust hits our aircraft and pitches it up, well, then I keep the stick straight up and my elevator is down, so it would lift the tail back. If it would go this way, it would push the tail down. If I would be banked by a gust from the side, then due to the banking and keeping my stick straight, this aileron is up, pushes the wing down, this aileron is down, pushes the wing up. On the other side, if I want now to move the aircraft around, then I have to do just as if the stick would be fixed on the aircraft and I want to move the whole aircraft with the stick. So if I want to go, for instance, into a left-hand bank, then I would take the stick and want to move it this way. The moment I do this, I lift this aileron up, this down, and the left bank is there. If I want to turn it, then I have to use combined rudder, which I have on the feet. That means I make a left turn, then I push the left foot forward and push the stick over to the left-hand side, and there is my turn, as you see it here. You see, this system is actually very simple and you can conceive it intuitively. You don't need to think about it. And this is important to fly, because when you fly, you have to think on other things. And you're controlling which you do without thinking that you do have to do this. You do it just intuitively. Now, a large aircraft, as we have it now, wouldn't be very easy to be controlled by hand, because these surfaces have quite some pressure on it. And therefore, we need some help to move the surfaces. So we have servo mechanisms and servo motors in between, which are controlled by the control itself or are controlled by an autopilot. This autopilot I can show you. You see, at what we conceived here and what we have shown is that when you fly through disturbances, the only thing you have to do is hold the stick straight up. Keep it always in the vertical position. If you do this, then the aircraft would by itself do the right motions. Now, to show you a simple model of the system of an autopilot, I have here a little arrangement with a free gyro in it. That means this gyro is on two gimbals. It can move forward and backward and sideways by itself. And when you wind it up, with a little electric motor, and down here is a big wheel which makes actually the gyro. We have then an artificial stick, or what we could call also an artificial horizon. So if I now move this model all around, you see the gyro keeps this stick all the time straight. And this system of a free gyro is the heart of an autopilot as we have it in the large aircraft. We use it also in the same way for having an artificial horizon so that the pilot can fly without any visibility. You connect this gyro with little wires so that he gives signals to servo motors which then operate the controls. You see? You shouldn't upset it. Now, to show you the action of the control system as it affects the flow, we have some models in our smoke tunnel. And at first I want to show you the action of a usual elevator or pitch control system. You see, I have here a model where the wing itself is not attached to my controls. I can only move this little flap back there, which actually is the same as an elevator flap. And you will see that I will be able now to turn the whole wing just by moving this flap. Let's put it back into the tunnel. So, and close the window. And when I now turn the blower on, I can demonstrate to you how this acts. You see, I have here this one control wheel where I can now turn the elevator up and down. You see, when we have now the wind going and I turn up, elevator up, then we increase the angle of attack. If I turn it down, I decrease the angle of attack of the wings. And I can do any adjustment of the attitude just with this little flap. If we now turn the smoke on, then we can even see it with the streamline around this simple aircraft model. You see? Now I decrease the lift. Therefore, our stagnation point sits up here. We have practically no lift. I turn it up and the lift is increasing. You see how much curvature we have up here and how high the velocity gets on the upper surface where we have then the suction. Another thing, it's interesting to see here, the change of the attitude changes not only the field behind the model, but the whole field. And it reacts for our eye instantaneously. Now I have another model in the tunnel which represents the aileron system. That means just a simple wing section with a flap back there, which I can also move with the controls. And if we take this model out and put it in, I will demonstrate to you that such a flap works the same way as if you would change the angle of the whole airfoil. Because when you move the flap down, actually you make more camber, and then the angle of attack is this way, while it was before this way. So you increase the angle of attack and you increase the camber, and in this way you increase the lift, or you decrease the camber and decrease the angle of the attack, and then you have down lift, or practically negative lift. So if we put this in there and see it with our smoke lines, then we can at once observe the action of a flap as it is used on ailerons, and certainly also on the elevator or on the rudder, in this way on the symmetrical section, while this is the wing section. Now let me adjust this. You see, I have to move both wheels when I want to change the angle of attack. And when I move only this one, then I can turn the flap itself. Now let's have some wind on and some smoke. This would be, for instance, a position of normal flight. You see, if I now turn it down, we have much more lift. If I go up, we have practically no lift. And you see also again how instantaneously the whole flow field responds to such motions. The motion is also the same if I have a larger angle of attack. The next time we want to talk about the propulsion systems which we use on aircraft. And I want to show to you, just as an introduction of this program, a picture which we took long time ago of a jet taking off. It's actually taken in 1941 of the experimental high-speed aircraft, the 163A, which I designed in way back 1938. You see, with these modern propulsion systems, we could have a very high performance, and actually we flew with this aircraft in 1941, 630 miles per hour. Now, I will also show you several models and other arrangements in the wind tunnel and here to explain to you the system of propulsion as with propellers and jets and things like this. For today, goodbye and auf Wiedersehen. Let me tell you a little fairy tale. Once there was an old windmill, and when the wind blew across the country, its arms moved around and around, and it roared for all the people in the country. And this went on for a long time. But finally there came a smart man, and he, believe it or not, took the windmill off and made a propeller out of it. Now, what is a propeller and how does it work? Well, we could, for instance, imagine it as just wings. Instead of going each one forward and making lift, they go around. And while they go around, they also produce lift. And this lift of each of these wings is transmitted to the shaft, and on the shaft it gives then what we call the thrust of the propeller. Thrust and lift are actually the same thing. On the other hand, since now such a propeller has the task to pull an aircraft through the air, this propeller moves not only around, but it moves also forward, and it screws itself into the air. if you would think the air would be a solid matter, then each revolution would give the propeller a certain amount of forward motion, what we call the pitch of the propeller, like we call it a pitch of a screw. Well, therefore, now, this wing couldn't be just straight, but it should be warped, because the outer blades make a much larger peripheral way, while all the inner ones make just a small one, while all the parts have to go with the same speed forward. Therefore, it is a wing on a spiral surface. Here you see a spiral surface like this, and you can imagine that each of these little sticks represent the position of a propeller blade while it goes once around. And we have to put then the propeller on such a surface which is here steep and there gradually or more flat. We can see that also if we take a propeller model like this here. Look at it. You see that this is warped, and we have inside the steeper angles and outside the more flat angles. But itself, if we take a piece out, we see that each section looks exactly like a wing as we had our wings in the smoke tunnel. Now, to observe the action of such a propeller, we have here a model in our wind tunnel. This model is just a tiny propeller driven by a small electric motor. You know, we have only 3 inches width in this smoke tunnel, so this propeller is quite small. You see it here mounted in the tunnel. And when we now turn the electric current on, then you see it runs and draws the air through the tunnel. If we start now the tunnel itself and produces some smoke, then we see at once the flow picture around a propeller. Isn't it interesting? You see, in front, the air is sucked into the prop and is accelerated actually before it hits the propeller disc. And then behind it, it again is pushed out. So we have a pressure differential across the propeller which pushes the air backwards. You see it even probably better if we just cut the speed off and let the propeller itself make the flow through the tunnel. Now we can also turn this propeller and give him angle of attack, and then we have the action as a helicopter rotor, which is nothing than a propeller which is now inclined to make lift and propulsion. You see it here very well. And we also can take a little less speed that you see this action more distinctively. But the best we can see it if we look at a slow motion pictures which we have now here. There it is. There we see the propeller in the smoke tunnel and taken with high-speed pictures. We have also pulsated the flow so that you can see the velocity distribution across this propeller. Now we have the same propeller in an inclined position, and we see now very clear how we could make it lifting and propelling. You see, the shift of this timeline is actually the same as we had it with the high lift wings. That means we have lift here. And also thrust, since the propeller is inclined, so part of the lift is a horizontal component which pulls the thing forward. That is like a helicopter would fly. We have seen the last time at these pictures in the smoke tunnel that we can use a propeller not only for a propulsion device but also as a lifting device, and we have even seen this in the slow motion pictures with the pulsating smoke, how the flow went over and gave lift and forward thrust. Now here we want to make a little test to see how much such a propeller would lift. We have a little model propeller here driven by an electric motor, and this is fastened to an arm which moves around here. And there we have a weight which we can shift so that we can finally load the propeller so much that it just barely lifts this weight. Now let's turn this prop on. You see, I have here a power supply, and we can see here the voltage and the amperage which we put in this little motor. You see, now it has about 10 volts, 15, 20, 25. There we are. So it lifts at 28 volts. You see it floats. Now you can shift that weight over there and give a little bit more power. Now let's shift the weight further on. And still lifts. Now let's put the weight here. There we are. Have it so loaded, so much loaded, then it wouldn't lift itself anymore. So that's the limit with all the power on. As you see, 33 volts. Now, can we do better? That's the question. Well, let's think about it. First of all, you see, when this propeller turns around, then it makes pressure underneath and suction above. That means it has a differential pressure across its disc. And since there is open air on both sides, this pressure on underneath will equalize against the suction which you have above, and you will have a flow around the peripheral line of this disc. So you lose some of the pressure which we have from underneath. What could we do about it? Well, if we put a tube around, then this pressure could not equalize around the tips, and we would have more lift of such a propeller. We should house it. Such a housing we call a shroud. That's like this piece here. See, and we can put this shroud around this propeller and then try whether we wouldn't have more lift if we put the whole thing in a tube. You see, we can put it over here. And we can try how this propeller within the shroud would lift. Actually, I have the weight at the same place where the open propeller didn't lift anymore. And I have put the shroud on it. which also weighs something at least. Now let's try. You see, we begin with low power and turn it up 15, 20, 25, 30, 'Aha! We don't even have the full power on, and it lifts. That means we have increased the lift of the propeller considerably by putting just a shroud around, housing it. Actually, this lift increase in a larger scale is in the range of 60% more lift. Now, to explain it to you more particularly, especially the flow condition which we have around such a shroud, we can see again a shrouded propeller in the smoke tunnel. So we have put a little shrouded propeller in our smoke tunnel. Actually, that is the propeller model which we did have before, you see, and on both sides we have put a wing-like section on it so that we have a channel through which the flow has to go now. We couldn't make a round shroud, otherwise you wouldn't see the flow inside. Now let's start the tunnel and the smoke. And we might see then how this propeller works. Here you see it first without the action of the propeller. You see that there is quite a bit of drag behind it because that wake shows that there is turbulence which makes drag. Now if we start the little propeller, watch this. Then, as you see, large part of the air is drawn into the thing and accelerated, and also the outer streamlines come near to the sections so that we have practically no drag due to turbulence over the shroud. We can even see it better if I stop the smoke as it looks here, to see how strongly this pulls. And when I turn now the model, then we can see it, how it would work with an angle of attack. So as a propulsion and lifting device. But all these actions you observe even better if we go back to our slow motion pictures. And there you have it. Here first, the action of the shrouded propeller as a straight propulsion device giving only forward thrust. You see how the air going towards the shroud is propelled because our timeline bends forward in the center. Now if we have it inclined so that you see at once the velocity field around such a device, and you see very clear that we have lift as we had lift on the wings because we have the shift of the timeline. You see on the other hand how this air which goes through the shroud itself is propelled and comes out much earlier, the little smoke cloud, than the other smoke from the timeline. We see therefore that such a device can be used as a lifting and propelling agent for an aircraft. The shrouded propeller is the simplest example of what we call an internal flow system. That means a flow which now is completely enclosed. And since we have it enclosed, we can guide it as we want it. And as we have seen, first of all, it is the most efficient lifting device. On the other hand, it is also high efficient in forward motion. Well, this brought me to an idea to take the shrouded propeller as the design element for an aircraft which would fly now without wings. And we call it the Aerodyne, that means a dynamic flying airship. Just look at this little picture here. I will explain it later to you more carefully, but to give you a glimpse of it, there our Aerodyne model consisting of a row of 4 shrouded propeller flies through the hangar in a test flight. It's propelled by 4 electrical motors, as you have seen it here in our little model. We can use the propeller also for another purpose. You see, we have seen that when we put the propeller in the tube, we have a larger pressure differential across the propeller. And if we make a very efficient propeller, then what is it? It is actually nothing than a compressor. Now, the main thing is that the pressure differential is as large as possible. And therefore, instead of using just 2 blades, as a usual propeller has, we can use several blades, which then cover most of the area of the propeller disc, as you see it here. We have here a tube with electrical motor and a little multi-blade propeller, which we also call an axial blower or a one-stage axial compressor. You will see that with such a device, you can even get a, well, good pressure differential in one stage. I will show it to you here. See, we have here our pressure gauge as we used it before. And if I turn the power on, then we can read the pressure differential across the propeller. See it here? Now I turn the power on more and more. And you see it gives a nice pressure differential of about 2 inches of water. Then if I close it down so that less air goes through, then this differential gets even larger. Now what we do here with one stage in a simple little model, you can do in larger size, and you can put several of these compressor stages behind each other, and in this way create a large compression. And when you then take the air which you have compressed, heat it up and blow it through the turbine and let the turbine run the compressor, then you have what we call a jet engine. A jet engine is actually nothing than a multi-blade shrouded propeller, which is here called the actual compressor. This is this part of the jet engine. Now, due to these many stages, there are jet engines up to 14 stages in this compressor. You get a large pressure ratio from the inlet to the outlet of the compressor, where we now blow the compressed air into a combustion chamber, burn it, increase the volume, and then blow this hot gas against a turbine, which takes part of the power out of this heated flow, turns it back through the shaft into the compressor, so that you drive the compressor with this part of the power, and the other power goes out as the jet stream. The thrust actually is produced by the compressor part of the jet engine and partly by the inlet. I will not go too far into the explanation of this process, which is actually in many ways more thermodynamics than aerodynamics. I just want you to realize that a jet engine is actually also a propeller device, since it has these compressor stages which are nothing else than a multi-blade propeller. Now, to show you such action in the smoke tunnel, we couldn't put such a device with these many blades in our tunnel, and we have made this simpler. We have made a small model of a jet engine, the cross-section of it, and instead of driving it with such a complicated device, we have a little jet stream in it. Now here we have the model in the wind tunnel, and at the present time the blower is not yet on. Now let's turn on the blower, and you see at once that the propulsion which we have inside gives us a strong stream behind and also pulls all the outer air towards this body and smoothes out the flow. A very interesting effect. You see, when I turn the speed down, then even this effect gets stronger. Now we can also show it with angle of attack, and there you see it. But the better representation is when we look at the slow motion films of this device. Now we see the jet model in the tunnel in a straight attitude, that means with no angle of attack. We took this picture with the so-called pulsating smoke, and you see in this way very well the velocity. First of all, you observe that the stream which goes in there comes out much earlier due to the inner propulsion. You see back there this puff coming out. And on the other hand, you see how nicely the outer streamlines follow the outer shape of this jet. This is due to the fact that the jet stream back there stabilizes the flow. Now you see it with angle of attack, and you can observe the same effect. It's very stable and smooth. And on the other hand, you see now that we have lift, because we have this shift in the smoke front, the so-called timeline. That means we produce here not only the jet stream inside, but we also produce a lift due to the flow on the outer surfaces of such a propulsion system. That is also used to make what I told you once, this aerodyne. The last of the propulsion systems which we want to mention here is the rocket engine, which will probably carry men into space. It can therefore not be an air-breathing system, but it must apply the oxygen and the fuel in two different lines which come into a combustion chamber and then get burned there and blow out a high-speed stream into the air. You see such a thing here in the smoke tunnel. In our next program, we will talk about the drag as it exists on bodies and wings. And to introduce this to you, we have here a body in the wind tunnel where you see what we saw before, the big disturbance which is caused by such a body. But we have also done a trick. We have inserted here a little jet stream, and if we turn on the jet stream, you will see that we can reduce the drag. That means if we compose a body with the right propulsion system, we have an advantage of such a combination as you see it here. And this we will explain at the next program. Goodbye and auf Wiedersehen.